Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Homework, Lesson 109. Okay, problem number 1. Calculate the current through the circuit below using Ohm's law and the formulas for parallel and series resistors. That's part A. And then we'll basically come back and do it all over again for using Kirchhoff's rules. So part A, that's fairly straightforward, right? So we're going to, let me just redraw the circuit here. No need to. No, I guess we will. Some potential V. We've got a little R1 here, a little R2, and then R3. So if I consider R2 and R3, I can calculate an effective resistance for that, or an equivalent resistance for that, using the standard formula for two resistors in parallel. And so that's just going to be the product, R2 times R3, divided by the sum, R2 plus R3. Then Ohm's law basically says that V is equal to I, the current, times R, where R is going to be, we're going to use the series formula this time and simply add R1 plus this equivalent resistance here for the parallel resistors. So it'll be R1 plus R2, R3 over R2 plus R3. And then we just need to solve for I to get that I will be equal to V divided by R1 plus R2, R3 over R2 plus R3. Okay, so that was pretty easy. Part B asks you to calculate this using Kirchhoff's rules. And so here we'll use, I'll assume that we have a current I going through this resistor R1, and then it's going to split off into two, I1, and of course we'll have I2. And if I chose the directions for the current wrong, the equations will of course correct that for us. So what are the equations that we can write down using the loop rule, Kirchhoff's loop rule? Well, we choose that I just call it I, equals I1 plus I2. Actually, let me just call, I'm going to call this I1, this I2, and this I3. I2 and I3. What else do we have? We've got, if we take the big loop, let's look at the little loop first. So we'll go around the circuit through here, through R1, and then through R2, and then back to the battery again. So what is that going to give us? That will tell us that V is equal to I1 times R1, plus we'll also get a voltage drop of I2 times R2, and then we're back to the battery again, and that's our V here on the left-hand side of the equal sign. And we just need one more circuit through here. I think I'll choose the little loop right here, the one that goes, we'll start at this point here. We'll go around the loop through R3. No, I'm sorry, we'll go through the loop around through R3, and then back up to this point where we'll go through the resistor R2 backwards and back to where we started again. So there'll be no potential difference around this, right? So we'll get 0 equals, because there's no battery, I3, R3, and then when we go across R2, we're going in the opposite direction of the current as we've drawn it. So this will be minus I2, R2. Okay, so now all we need to do is set this up into a matrix and solve. So we'll have 1, minus 1, minus 1, 0. We'll have R1, R2, 0, and V. That's the second equation. Then the third equation we'll get 0 minus R2, R3, and 0. Now we just need to manipulate this. And so the first thing I'll do is I think I'll subtract R1 times the first row minus the second row. So the first row we'll just keep. The second row, however, we're going to get rid of that leading term, that R1, and I'll write down my notation that I like to write down here. We're going to do R1 times big R1. That means row 1 of the matrix, by the way, minus the second row of the matrix. And if I do that, R1 times 1 is just R1, and R1 minus R1 is 0. And so we'll get 0. Here we're going to get minus R1 plus R2, And then here we'll get minus R1 because of the 0. And here we'll just get minus V. And then we'll leave the second row unaltered. So it'll still be 0, minus R2, R3, and 0. Okay, so let's manipulate. Now we want to get rid of the term right here, this minus R2. And that's going to be a little bit ugly. So let me reproduce the rows that we're keeping. We'll still have this row, minus R1 plus R2, minus R1, and minus V. And so the row operation we're going to do here, I didn't really leave myself enough room to write this. Here's what I'm going to do. I'm going to multiply minus R2 divided by R1 plus R2 times row 2, and I'm going to add that to row 3. So that's the operation I'm going to do. And when I do it, I'll get 0 here, of course. It'll get rid of this minus R2 term for us. But here I'll have R1, R2 over R1 plus R2 plus R3. And then in this entry here, I didn't really give myself enough room. I'll have R2V over R1 plus R2. Kind of ugly, but no worries. If we then solve, because this, remember, this is the I1 term, this is the I2 term, this is the I3 term. So if I solve for I3, I'm going to get R2 times V over R1, R2 plus R3 times R1 plus R2. And then if I solve for I2, using this for I3, I'll get R3 V over R1, R2 plus R3 times R1 plus R2. And of course, I1 is equal to I2 plus I3. That's our next step. So we'll plug these two currents, we'll add these two currents up and plug that into Ohm's law. And so we're going to get something like I1 times R1, R2 plus R3 times times R1, sorry, R1 plus R3, R2, just expanded out this, this term here, divided by R2 plus R3. And that, of course, is going to be equal to V. This is just Ohm's law, using this sum here. But I can manipulate that, write that I1 times R1 times R2 plus R3 divided by R2 plus R3 plus R2, R3 over R2 plus R3 equals V. And then I can simply solve for I1. Am I still on the camera? No, I'm off the camera now. That's what I thought. I kind of ran out of room here, so I will put the solution up here. I1 is then going to be equal to V divided by R1 plus R2, R3 over R2 plus R3, which is exactly the same thing that we got just using the formulas for series and parallel circuits. Granted, using Kirchhoff's rules was much more algebraically intensive. I don't know if I got everything on the camera here. Can we see this down here? No, I guess we can't. I could move it a little bit so you can. There, this was the kind of the last algebraic step right here. Sorry about that. Okay, that's a tough one. Okay, for all the remaining problems, the number 2, 3, and 4, the routine is the same. We're going to find the current through each resistor using Kirchhoff's rules, and then map the power supplied and consumed. So basically say how much power the batteries supply or consume if they're being charged, and how much power is being consumed by the resistors. So let's start with number 2. Let me just draw the circuit for it here. Number 2. Okay, we've got 9 volts. Here, this will be 0 volts. And then here we've got 3 volts. So a bit of a funny setup. if you didn't catch it, these batteries are hooked up kind of funny, right? Got a resistor up here. We'll have a resistor right here, and then we have a resistor along here. And this is, let's see, 1 ohm, 2 ohms, and 1/3 of an ohm. Okay, so how do we proceed with this? Well, I'll use my current tracking routine here is going to be something like I'll have a current I going through this resistor, and then I'm going to have a current I1 and a current I2 going through these two resistors. So these are just points at which it splits off. So we start with a current I through this 1 ohm resistor. We get to this branch point right here, and we go a little bit this way, and we go a little bit this way. And so the one going this way will be I1, the one going this way will be I2. And these are the directions that we're going to stick with. So what are the equations? As always, we'll use the current rule, that the I is equal to the sum of the two currents at the branch point. We'll also have a rule. We'll use Kirchhoff's loop rule on, let's see, what are we going to use here? We could go through, have I go through the 1 ohm resistor and then back through the 2 ohm resistor, picking up a 9 volt increase in potential. So we'll have that one. So that'll be I plus 2I1 equals 9. And the other loop we will do we'll go, let's see, what's a good one? I think what I'd like to do is I'd like to go around here. I'll start at this point here, go through this resistor, this 2 ohm resistor backwards, and then through this 3rd ohm resistor and through the battery. So that's going to give us something that looks like this. Notice that we're going through the battery backwards. We're going through the positive terminal first and then to the negative terminal. So this is going to look like minus 2I1 plus 1/3 I2, and this will be equal to minus 3. Why minus 3? Because we went through that battery backwards. And so these are our three equations. We can set them up in matrix form, and that matrix form will look like this. 0, I think I want to, oh, not 0. We'll do this one. 1, 2, 0, and then 9. And then the last one will be 0, minus 2, 1/3, and minus 3. Okay, so the first manipulation I'll do is I'll take R1 minus R2, so first row minus the second row, leaving the first row intact, getting rid of that leading entry there. That will give me minus 1 minus 2, of course, is going to be minus 3, and minus 1 here, and then minus 9 here. Leaving this row unchanged. 1/3, and then minus 3. And so the row operation I did was just R1 minus R2. Next, let's write in what we're not changing. 0, 3, 1, 9. We'll do 2/3 times row 2, add to row 3. That should get rid of the minus 2 here. So I'll give you 0, 0. That will make this 2/3, make this a 3. Excuse me, a 1. Yeah, a 1, and then this will become a 3. And I also, by the way, I multiplied this by a negative number. So I'll do minus R2. So I just changed the sign of R2 throughout. And then I took that and added it 2/3 times row 2. So 2/3 times row 2 minus row 3. It depends on what you want to do, if you want to do that after the fact or not. But that's fine. And so now we're basically ready to solve. So we can solve for I2. And it's already solved. It just says that I2 is equal to 3 amps. And then I1 is going to be 3 times I1 plus 3 amps will equal 9. So we have 9 minus 3 divided by 3 gives us 6 divided by 3. That's just going to be 2 amps. And then I is just the sum of these two. So I is just 2 plus 3 equals 5 amps. Good. Now we can go through and we can do the part B and map out what's going to happen. So what I would do for this is I would use, on each of the resistors, I'd use the formula I squared times R. That'll give me the power. And so what we'll end up getting, we'll have, see, 5 squared times 1 ohm is going to give me 25 watts. Then I'll have 2 times 2 squared will give me 8 watts. That's a 2 ohm resistor. And then, of course, 3 times 1/3 amps squared will give me 3 watts for a total of 36 watts power consumed. And then for the batteries, we'll do V times I squared. And that will give me 45 watts. But the 3-volt battery, it's charging, so it's going to be consumed power. So we'll call that minus 9 watts. And of course, 45 minus 9 is 36. So these two have to balance out. So I could call this minus 36 watts if I want to put negative signs in front of all that for consumption, and plus signs for the ones where it's producing power. And so we produce 36 watts total, we consume 36 watts total. Okay, and that's basically what we're going to do on all of these problems. Okay, for number 3, we're doing it for a circuit that is almost the same as the circuit we just did. So I'm just going to make a few changes here. For starters, I'll get rid of the battery part here. So this will be problem number 3. And this time, the battery configuration is like this. So we'll have the 0 volts down here, 3 volts here. Really, you could think of it like this, 3 volts here, and then 12 volts here. Okay, so that's really the only difference. I'll keep the currents the same as I used them before. Equations that are the same, almost all of them are the same. The voltages are different here. So how would we set this up? Let's just write it in matrix form right out the gate. So we'll have, of course, 1 minus 1 minus 1 and 0. That's just, I equals I1 plus I2. And then we'll take the big loop around, or excuse me, the middle loop around, going from through the 1 ohm resistor and then across to the 2 ohm resistor, so the I1 current. And so we'll get 1 ohm here, and we'll get the 2 ohms here. We don't go through the third resistor, so 0 there. And we get 12, I'm going to write as 12 minus 3. Because remember, the potential here at this point, before it was 0, this time it's 3 volts. And then the last loop will be the loop down here, and that will again be 0 minus 2 and 1/3. And this time, positive 3 volts, because we changed the direction the battery is going. And so, again, matrix manipulations on this. I'll kind of cut out the discussion of it because it's all the same, right? We just do the same thing over and over again, but in case you get stuck, I'll show you my work. And so what did I do here? I did R1 minus R3, and then down here I did 3 times R3, just to make some changes to make things a little bit easier. And 0 minus 9, 0, 3. So what did I do here? I did minus 2R2 plus R3. And that allowed me to solve, finally, for we have 3 times I2 equals 27. So that gives me that I2 is going to be 27 over 3, or 9 amps. And then what about I1? I1 is going to be equal to 9 minus 9 divided by 3. This is 0 amps. And you're probably going, what? How can you get 0 amps? And of course, I is I1 plus I2, so I is just going to be 9 amps. So what's going on here? Well, you can think of it this way. You've got a current from the 3-volt battery flowing this way, going that way through the 2 ohm resistor. But for the 12-volt battery, we have a current I1 going in the opposite direction. Not necessarily well, they are the same, but in opposite directions. And so these two currents basically cancel out and you get no current through this 2 ohm resistor. So it's a bit of a trick problem. The power consumption and production, what's that look like? So the I squared R stuff, what are we going to get? We're going to get 9 squared times 1 ohm equals 18 watts. We'll get 0 squared equals 0 watts for the 2 ohm resistor. And then 9 squared times 1/3 equals 27 watts for the 3rd ohm resistor, giving me a total of 108 watts. And then for power production, we got VI. Well, 9 times 9 is 81 watts, plus 9 times 3. 9 is the amps, the current I, giving me a total of 108 watts. So we produced 108 watts, we consumed 108 watts. Okay, number 4. This one I got from my my notes, And I'm not sure where I got the problem from. I didn't design this one myself originally, but the numbers work out nice, so that's why I like it. So let's look at this circuit here, number 4. So let me just copy it down here. Got everything? Looks like it, yes. Okay, so the current scheme I'll set up, I'll have I going through this 4-volt battery and 2-ohm resistor, also that 1-ohm resistor, and branching off this point here, right, in which, or I guess I can draw it this way this time. We have I going like this, and we'll have I1 going down this area, and then we'll have I2 going through this branch in these directions. Okay, so starting with our currents, the sum of the currents, and then we'll have we're just going to add these 2 resistors up, even though they're on opposite sides of the battery, okay? So it's 3 ohms plus 1 ohm, that's going to give me, or 2 ohms plus 1 ohm, that'll give me 3 ohms for I. That can be confusing, but it doesn't matter. We're going to account for the 4 volts and the 8 volts separately. That'll be on the right-hand side of the equation, but we'll look at that last. But let's just look at the sum of the resistances we go through. We've got I going through 1 ohm and then through 2 ohms, so that's the 3 times I right there. But we also have a 2 ohm resistor for I1, so we'll have 2 ohms for the I1 entry. Remember, this is I1, I2. And then these over here are the voltages. And then nothing going through the 3rd resistor. And so the sum of the voltages around this, though, if we look at it, right, what do we have? Well, we've got the 8 volts as we go across this way. So that's plus 8. And then we have plus 4. But when we come through here, we go the wrong direction through this 4-volt battery. So that's minus 4. So we have 8. So I'll write it as 8 plus 4 minus 4, which is going to give us just 8 volts. And then for the last one, I think I'll use this loop here. So I'll write that as nothing going through, no resistors for I, but I1, we're going to go through the 2 ohm. We'll go in this direction, which means we're going to go the wrong way across the battery, but that's okay. So we'll write 2 here. Then we go across the resistor, but we're going in the wrong direction, right? Because we're going around counterclockwise here. So this will be minus 6 for the 6 ohm resistor. And then we went across the battery backwards, so that'll be minus 4 for this entry here. And doing row operations on this is fairly straightforward. And so what do we have is 3 times row 1 minus row 2. And then 3rd row, just divide it by 2 just to make things a little bit easier. So the 264 here. And then finally, and this was a result of doing 1/5 R2 minus R3. And so this gives me that I2 is just equal to 1 amp. I1 is also equal to 1 amp, which means that I is equal to 2 amps. And so the power consumption through it, let's look at it. Here I'll just write it as the batteries, and then I'll write the resistors over here. So we'll have 18 watts, right? This is using I squared V, and this is using I squared R. 18 watts, 8 watts here. We've got minus 4 watts going through the battery backwards for a total of 20 watts production. And then the resistors will have 4 watts consumed, 8 watts, 2 watts, 6 watts. Adding all that up, we get 20 watts of consumption. And so everything works out just fine. Okay, that was the homework in exercises using Kirchhoff's rules. I didn't put too many on here because they're a little bit time consuming with the algebra. Hope you enjoy them.